good morning everyone from me too, and welcome to the first plenary session. My name is Angelina Bekasova. I represent here the Ministry of Economics of Latvia, and as a short intro, I'm that person who is going to connect everything and everyone to space. Some people in the audience already know what I'm talking about, so sorry, not sorry, but we are part of the space sector today, us all, you want it or not. What we want for sure is to use the benefits the space sector is offering us right now, what we have already in our hands, and to listen to the next keynote by Dr. Thomas Brunschwiller. Thomas works for IBM Research Europe, based in Switzerland. As an American company, you know IBM is behind lots of groundbreaking technology. IBM Research Europe involves Europe in this whole story, obviously, and has access to the most exciting research topics, starting from quantum, continuing to AI, and of course, space technology. Thomas is the principal researcher and research manager leading AI for Climate research team. He shared with me that it's cool to work for IBM because IBM gives you access to different topics for research. So his background is quite broad, spanning from physics to AI. A fun but quite serious fact, Thomas holds more than 60 patents in different disciplines, and of course a list of scientific publications, including in Earth observation. Thomas' presentation will be very much related to artificial intelligence. And as we know, in artificial intelligence, somehow large language models made sense, magically sense of our world, of ourselves, of the information we have generated and we want to generate. And that all through words and meaningful connections of words. And now we hold terabytes, if not petabytes, of satellite data daily. So isn't it the most logical thing to apply the same AI to make sense of this data? And Thomas will be talking about tokens. Here, tokens would be pixels or clusters of pixels, just as words or clusters of words or letters that make sense to us. Embeddings? Well, Thomas will explain. Thomas, welcome on stage. Tokens and embeddings, the new Lingua Franca for exploring planet Earth. Good luck, and good luck.
Thank you, Angelina, for the welcome, and hello, everybody. It's a pleasure to be here, and I like to try to do an experiment with you. So maybe at the end of the presentation, you think like machines in the space of embeddings and so on. So that's why the title, from an AI model perspective, embeddings is really the new language for those models. And maybe we have some benefits if we think the same way and design our systems accordingly. But first, yes, I'm from IBM and working in the strategy of climate and sustainability. We are tackling many foundation models in science and engineering. So here just some are listed. Our main focus is on Earth observation, together with ESA, PhyLabs. But then also with NASA, we look into lunar and helio, as well as weather and climate foundation models representing physics. And we also recently launched foundation models for the electric grid, taking into considerations similar principles from the other domains, basically getting speed-ups, getting faster insights with less annotations. So here, big data is definitely present, as we've heard from the previous speakers. We have all this wealth of satellites out there monitoring planet Earth on different resolutions, different timescales. And yes, it's a lot. So data sets are reaching levels of 800 petabytes, and we have to be able to compile insights out of those data sets and also to transfer the data. There's a rich variety of applications those data sets and observations can provide. And typically, we have built models for each of these individual applications. So the question is then, is this sustainable? If you look back maybe 3 years before the ChatGPT moment, people have also built language models, maybe to translate, another language model to summarize, and so on. But then, with the foundation model breakthroughs in the language world, we are now able to use one model and to dictate through prompting and maybe some examples the specific task for a given model. So could we do the same also in the Earth observation domain? So that's the challenge we set out. And again, remember, we have petabytes of observations, but we may not have a lot of annotations. Again, you need experts annotating certain specific events and quantities, and the data sets may be very limited, maybe only in few local regions, and accordingly the models would not generalize well. So that's why we thought, okay, let's use the paradigm, use self-supervised learning for language models, apply to the foundation models here for Earth observation. So the blue box would be a general model, which then can be updated for specific tasks. This brings me to the foundation model for Earth observation, which can be considered like an AI model as a service, which is a platform to serve multiple applications. So how we go about it? So first, there's the compute-intense part of the whole endeavor. So we sample data from the wealth of satellite imagery we have. And maybe here just a side note, if we think about ChatGPT or these large language models, so they may have been trained, depending on the models, from 40 terabytes to maybe 100 terabytes. And just before I mentioned to you that we have here 800 petabytes in principle as a community, which is too much. So we have to do some clever sampling of the data. We filter the data, and then we feed the data into the model. And analogous to the language models have to predict the next verb given the context of the paragraph. So we do the same thing here, but here we're in the image domain. So basically we have our basic image as an input. We blank out certain parts of that image, so we call them patches. And the model is an encoder-decoder model, which then tries to reconstruct the blanked out data. So that's how the model tries to understand the underlying data and probability distribution as a pre-training task. So this can be done fully automatic and does not require any annotation. So that's the beauty. The model has seen the diversity from the planet without human intervention. As a second step, you may want then to fine-tune the model with your few annotations you have, using the encoder you have trained up there. Now it's frozen, so that's indicated by the blue color, and you train another decoder, which is lightweight and can be adapted very quickly. Finally, you freeze both the encoder and decoder, and you apply it in your application. So here just an example of one of our first Prithvi models, which are adapted vision transformers to respect the multimodality of the satellite data and also the temporal aspect of satellite data. But conceptually, it's a model used in the vision domain. So we again blank out certain parts of the input data, we put it into patches, run it through an encoder, and now here it's the first time we meet the embeddings. So throughout the encoding, so with the encoder, kind of the original data gets encoded into a vector which stores the semantic information of each of these individual patches. So, and with these embeddings, the model makes sense or performs the analysis of the later downstream task. In this case here, it's the pre-training task, which is somewhat artificial, so it just has to regenerate the original data. But this is a very handy task because we can easily confirm if the reconstruction was performed well. And as mentioned before, the sampling has to be done cleverly, so we split up the world into different ecoregions and land classes, and then we uniformly sample from the global distribution there. Now, as we have the encoder pre-trained, so this may require maybe 64 GPUs for 1 week. So we collaborate here with Jülich Supercomputing Center, so they perform the large-scale model training. So we can then use this encoder and on just a single GPU adapt the model for the different tasks. This could be binary segmentation, it could be multi-class segmentation, for instance, for classifying crop species, or it can be a regression task. So this model is very versatile to adapt. And again, here the embeddings are the key part. So instead of the input image, in principle you could say, we could just store the embeddings, and all these decoder heads on the right side, they use all the same embeddings. So why not shipping around and storing the embedding, as these embeddings contain the semantic information from the original image and potentially can be compressed. So that's why I call embeddings the new Lingua Franca for these AI models. And you could consider to generate them once and reuse many times. And this is a bit different compared to the large language models. There, we hear also that AI may be a problem because it consumes a lot of energy. As everybody will submit another prompt, so it's usually a very, very diverse data which is sent around. But here in our archives, we have satellite images representing the planet from the past. And researchers are pulling from that data multiple times. So why not storing the embeddings and shipping the embeddings around? And here, this is kind of demonstrated here in our Embed to Scale project, Horizon project. We are exploring these opportunities. So basically, you may have a data center A with a specific satellite image type. You encode there the image, you store the embedding, and you ship then the different embeddings to a data center C where your application runs. So this has the advantage that there's less storage needed, potentially. There's less latency for transfer or egress cost. Then to infer, you just have to run the decoder head. That's typically much smaller. It's not a foundation model. And you can also take advantage of finding similar images in all your data set. So we set out to this goal and are exploring kind of the different spatio-temporal embedding landscapes from patch level or image level representations, but then also single temporal or multi-temporal aspects. So we have to figure out with the community what the best representation would be. And therefore, we set out the NUCO bench. This is a multitask evaluation benchmarking and evaluation framework, which is out there as open source, and we ran a competition at CVPR. The goal was to compress Sentinel-1, Sentinel-2 imagery from the 4 seasons to a fixed size vector with a 7000x compression rate to do image level to perform image level tasks. So that's one example, but we cannot go even further and say, hey, if we generate embeddings, we could also use entropy encoding to compress the embeddings even further. And there's neural embedding compression methods which take advantage of foundation models, so that's the blue part, which already was pre-trained, and we just have to additionally train some yellow layers, which convert the probability distribution from the embeddings into a probability distribution which can be compressed much better. So in this approach, you are shaping the embedding space to have higher compression rate. Now, if we are considering, as we also heard before, that there's many satellite information out there, some modalities may be missing in certain locations, some are accessible. How would we now deal with multimodal foundation models, incorporating different satellite modalities, and that brings me kind of to the tokens. Here you can see an overview about our engagement with ESA PhyLab. Together we built a TerraMine model, which is the first any-to-any generative, large-scale multimodal foundation model with state-of-the-art performance. As input, we are considering modalities like Sentinel-1, Sentinel-2, digital elevation maps, vegetation indices, land use, land cover classes, or even figure captions or longitude, latitude. Now the challenge is we have to transform the input into tokens. Tokens, as before mentioned by Angelina, so they are a very compressed representation of your input data. So you may have, for words, this may make sense to you much easier. So let's say cat would be maybe number 12, or dog would be number 16 in your vocabulary. So here we are translating patches of an image into a code book, which is a finite set of integer values. This is done before we learn then a correlation between the modalities. So we basically kind of simplify the input data such that the model can learn the correlation across the modalities and eventually also generate across the modalities. So first, as mentioned, the tokens are generated, so we have to use again a encoder-decoder model, now with also this diffusion decoder concept to generate data. So the raw input may be one modality, Sentinel-2, and the image is projected into a code book as before. You know, in this case, something like 16,000 tokens, and we reconstruct again as a pre-training task the original image. Once this is done for each of the modalities, we can pick then some of the tokens randomly, and the main model, which learns the correlation, has then to predict some sample target tokens by generating latent representations internally, and then we can, with cross-entropy, compare the output again. So this is the way we do the correlation learning, and the model can then be applied for many, many tasks where you input multimodal data, single modal data, and so on. And that's how it performs on the ESA Pangea benchmarking dataset. So we compare TerraMine base and large to other state-of-the-art foundation models. And in particular, as you can see, it's kind of the blue outer line indicating that the model outperforms most of the models most of the time, in particular for the multimodal test cases. So some test cases are single modal, so that's where other models can be on par or outperform TerraMine, but in particular for the multimodal applications, TerraMine is very powerful. And this is usually the case, so we want to incorporate all the context which is accessible to us. Now, another interesting aspect of TerraMine, as I showed you with the tokenization process, TerraMine can generate, and can not only generate the data it gets as an input, but it can also generate across the modalities. So for instance here, you could have a raw input, a Sentinel-2 image, that's the upper row, and then TerraMine could generate Sentinel-1, digital elevation map, land use, land cover, or NDVI profiles, just out of the box from this input. Of course, you know, we still need kind of additional satellites like Sentinel-1. It cannot replace Sentinel-1, but it just shows you the power that it can try to guess from the input what kind of the image would look like, and it tells you also kind of how much this imagery is correlated. So now, Turing test. I show you 3 images. One is a true satellite image, and 2 of them are generated by TerraMine. And I go through once, and then once again, and just for yourself, just try to figure out which one is the true one, and then maybe tonight, if you are a winner, then you can maybe get a nicer dinner or a drink, paid by yourself, sorry. Okay, so here image number 1. This is a Sentinel-1 GRD observation from Santiago de Compostela. Here we have the same location, Sentinel-2, L2A, or then the digital elevation map from the location. So I just go in reverse, make up your mind, which one do you think is a satellite observation and which one is generated? Easy or not? So the observation is the Sentinel-2 L2A image. All the others were generated. Who did figure it out? Please raise the hand. Okay, we have some satellite experts here. Yeah, but it's pretty amazing how well the model generates. And as we explored the model, we also figured out a pretty interesting aspect, and this is thinking in modalities. So if you have only one modality at hand, it can help if the model generates internally another modality, for instance, land use classes, and then you generate kind of maybe a flood extent. Then the performance is increasing. And this is similar to the large language models, which also do, which kind of do stepwise reasoning. So, but we are still exploring, you know. We call it thinking in modalities. We see sometimes the performance improves. And here I show you an example. This is an assessment we perform here close to Ellis Island, so the harbor in New York, trying to identify ships. Now, if we just use Sentinel-2 as a single modality, we identify some of the ships, but if we incorporate also, let me see, okay, so that should be here. If we now also generate internally the land use land cover tokens, so the model just internally generates it, and then we use also those tokens to make the predictions, then the assessment is much more accurate, and we get also the other false negative ships identified. So this shows that kind of these constraints, because the model knows where water bodies are, and that's also where you would try to identify ships, and then you could do the assessment, you know, how often what is the activity in the ports, etc. So that was pretty amazing to us. Right, so in the interest of time, I skip a bit this part, but I just want to say we are injecting now also atmospheric information into TerraMind. So basically, as of now, we have these individual images, but now it can be very interesting kind of to inject temperature, you know, temperature time series into the model. So we again perform some tokenization and then the correlation learning, and we already could see that there's quite some interesting strong correlation from Sentinel-2 to predict temperature profiles. So these are, again, early experiments. We just submitted an ICLR paper. Stay tuned, more to come here. But we should really move in this direction, that we incorporate atmospheric conditions and Earth observation together. Now, I just want to encourage you. Yes, Angelina, you introduced me with some patent portfolio, but the current world is much different. So I think that was from my first research life, working in physics and nanotechnology. But now in the AI world, we are super open. So we developed this together with European partners, with ESA, and put everything on as open source on Hugging Face, or it's accessible on GitHub. So try it out. Here you can get access on the IBM ESA Geospatial Hugging Face organization. You can play with TerraMind and all the different models. There's also the data sets available we used for the pre-training. We also develop libraries here to call out TerraTorch, which makes your life easier to deal with those models, to fine-tune them. So it's a low-code environment, enabling non-computer scientists to deal with the foundation models. So there's many tutorials out there, open source, feel free to use. Now, also important to mention, together with the PhiLab, we have the TerraMind Blue Sky Challenge out there. So if you're interested in to play with TerraMind, you may come up with some cool experiments, upload them, so we have 4 times prize money of 1,000 euro, so this time you get some money, you don't have to pay the dinner yourself, but there's a bit of more work to do than just identifying which image is right. Yeah, feel free to interact and reach out to me. So I hope I could give you a bit of an insight how these AI models think, namely in embeddings and tokens. So this opens up a whole new world, and we really want to explore together with the community, and we also have a demo later with Cloud Pharaoh in the afternoon, where we demo again how embeddings can be used to compress data and the foundation together with the foundation models to do real-time inference, and we have an example for Latvia for scene classification masking. Hopefully an interesting example, and we hope kind of to bring this also from the research state into operation realm. And with this, I'd also like to mention and thanks Philab for the support in the FastEO project where the TerraMine model was explored. Again, the European Commission also for the funding for the Embed to Scale project where we explore the embeddings. And thank you as well for your attention and for having me here. It was a pleasure. Thank you.
Thank you very much, Thomas. Now it's time for questions. Use your opportunity to shine and let's shine. Someone, maybe, raise your hand. No one, very good, because I had a question. You know, Thomas, several years ago, I started my space journey specifically with Earth observation data and policy making. But my academic background is linguistics. And I'm also somehow addicted to AI. So thank you very much for specifically your topic. You mentioned already, and I mentioned, that you get to work with a huge variety of topics at IBM. How do you approach that? Do you start always with a new page, or these are interrelated chapters? In other words, please give us advice how to survive in this new era of very fast and accessible innovation.
Yes, that's a very interesting question, and I think we could probably speak now for the next 45 minutes about it. But exactly, so I think it's super important in nowadays world, especially in the AI domain, things are moving lightning fast, and it's real challenge also for an organization like IBM to keep the workforce up to speed. So you have to engage with people and shape their mind to be open for the next technological innovation. So really reaching out and considering to explore the new technology. So we have internal programs which allow people to upskill. We have the freedom to explore, and also we invite individuals to be part of the organizations with that mindset. So I think that needs to be a given. But then usually in the transition from one domain into another domain, there's a lot of uncertainty. And then also from the management side, we need there some secure environment for individuals to also transition. You cannot expect from day one the same performance as the day before in the other domain. So there needs to be a transition period where you have some clear steps to do and provide the freedom to grow. So I think that's the way I perceive this within IBM. It's definitely a challenge because you start all over again, you go again to master classes at ETH and things like this. But I think it's just beautiful if you can dive into different topics. So, and it also broadens the horizon. And what we also learned is because you cover then different domains, you have more the system thinking, and sometimes also the innovation is kind of between the different domains in the grain boundaries. So there may be another advantage.
Thank you very much for your answers. So AI is not a threat to humanity. We still will need people and we'll rely on each other. So maybe someone has thought of a question.
Can you hear me? I have a question on the visualization and interpretation of embeddings. I've seen some discussions going on LinkedIn. Yes, embeddings are really only vectors. You shouldn't look at them as a human. You can't interpret them. On the other hand, yeah, these embeddings are there. There are ways to visualize it. It strikes me that in your presentation you didn't really do that. So yeah, what's your opinion on this visualization? Does it make sense to visualize it as an RGB? And what about the interpretability? Or can we use embeddings in a way to explain observations or the results of fine-tunings? Or can we use it to attribute, okay, this information primarily stems from this kind of satellite modality, and that makes the embeddings more powerful for this kind of application?
Yeah, thanks for this question. And indeed, I didn't show any embeddings visually here. In the afternoon, there will be a view from the TerraMind embeddings. So typically, these embeddings are multidimensional. So then it's the question, how do you visualize them? So one way you can do it is with principal component analysis. You project kind of this multidimensional space into some limited number of dimensions, but the most important ones, and then you can visualize them in color coding, for instance. So that's what I can show in the afternoon. And of course, kind of we use such methods also kind of to study what's going on in the models, etc. But ultimately, it's very hard to interpret what exactly is going on. And if we are searching for complex patterns, then it's not always clear that as humans we can easily display them or explain them. So, I was also working in the digital health domain, and there also some people were always asking about the explainability, but then some physicians were telling me, they could not even explain necessarily their judgment about certain, treatments themselves exactly. So I think, yes, we should understand as good as possible what's going on in the models, but I think it's more testing the robustness, coming up with benchmarks, demonstrating how they perform, and also testing how they perform with distribution shifts. I think the exploration of the embedding space visually is interesting. It helps to a certain extent, but I think it's a small fraction. Sometimes you can also see, for instance, in the language domain, there's like these fun games, there's this fun fact that you can project queen and the king into this embedding space, and man and woman, and then you can start doing arithmetic. So you can, for instance, subtract, you can take the difference between men and women, and you can add this difference to the king, and then you end up to the queen. So in some simple cases, you can visualize this nicely, but if the pattern becomes too complex, then it's hard. So, there's methods which, for instance, show you why a model would identify a cat to be a cat. And then typically, you would, on the image, you would see the pixels visualized which are in the area of the cat. But this sounds to me a bit blunt. So, maybe if you have a zebra and a horse, so the frequency of the stripes may play a role, but maybe then you have to project it into the frequency domain, and you cannot visualize this on the image. So I think, yes, explainability is very interesting and is part of it, but I think we use more the methods that we have this Pangea benchmark from ESA, for instance, which covers a large range of applications. We train the models and we apply them on these benchmarks, and also test, for instance, out of distribution, etc. But visualization is definitely one thing also which is interesting to also see what's going on the models. Does that answer the question, or just partially? Sorry, I did not see where it came from.
Here, yeah, I'm Joris Codé from Vito, by the way. Yeah, thank you. That answers my question. Indeed, I'm looking forward to the demo ride this afternoon then as well.
Yeah, it's cool. Maybe just like one last comment which was interesting, like when we had last year a discussion between physicists working on AI models for weather and the physicists who built the physics-based models, I mean the traditional forecasting models. So there was also the argument, you know, the AI models, they don't have explainability. But then it's also like, there's no single human on the planet which read all the code from those climate or forecasting models. So it's not comprehensible kind of to understand the entire code of such models. So then what does it mean to be interpretable? So in fact, kind of there was also discussion, you know, are kind of these large models, are these black boxes as well to humans? Do we only understand certain parts or individuals? So what is then the difference? I think it's very interesting, and it can become also philosophical at one point. But I think we have to make sure that models are robust. How do they deal with distribution shifts and so on? And this is something we have to now also prove in kind of the real world applications. So right now we're using these benchmarks, but as you hear also from the large language models, you know, you can overfit to the benchmarks. So eventually you have to prove in real world how it performs.
Thank you very much. We have time for one more question, if there is any. I see a hand. Can someone help with the mic? Yes.
Thanks so much, Thomas. What an interesting keynote to open the session. Just had a question on extensibility of the kind of frameworks that IBM are implementing in the domain. For example, at the end you were saying you're building in atmospheric or weather forecasting or realized atmospheric models into the foundation model. I just wonder about the order of the events. If I understand correctly, you're kind of extending the base that's built on land use from Sentinel to Sentinel-1, and you're adding in some more data sources. I just wonder if there's any risk about the way the embeddings evolve based on the order of how you add the data, kind of thinking around different spatial scales, this kind of thing. I don't know if you got the question.
Maybe I tried to answer. So I think the question was like which kind of modalities we may include and how we would deal with the different resolutions.
Yeah.
Okay, right, yeah. Exactly. So right now, one challenge is also we have these modalities, and then we do the correlation learning, and that takes quite some compute. And if you're adding additional modalities, you have to do the correlation learning all over again. So that's something we want to work on together with PhyLabs next year, to have also this plug and play mode that you can plug in kind of new, that you can extend the model without kind of starting from scratch with new modalities. That's one thing. The other thing is, as you stated, right, so as of now we had mainly imageries as modality. We also included text and longitude, latitude. We also represented as text tokens. So these were, let's say, a bit two different modality or types of inputs. And with kind of this, the sneak peek I gave you with the time series, there also we are using kind of tokenizations similar to the language world. So that's kind of this extension. I think we also want to expand then, considering Sentinel-1, also the imaginary part of the data to be included. So that's kind of this side. Yeah, I think that will happen already this year, or some of this, and then next year together with the community, and yeah, the models will then be available. One thing which would be super cool is, okay, so we have now maybe Earth observation, we have atmospheric variables in there. Interesting would also be kind of to input societal parameters. You know, we have the atmosphere, which behaves, let's say, according to physics, then we have maybe the Earth, which, you know, we have the biosphere, and then we have us, society, and somehow to have an Earth system model, it would be great kind of to think about how to also include those aspects as well, right? So I would invite you kind of maybe to be part of that journey.
Thank you very much. By the way, combining statistics and Earth observation data is very interesting topic for us. We're discussing it right now because there is a lot of data about us in Latvia, but we'd like to connect it to Earth observation. So now we'll know who to talk to. Thank you very much, Thomas. A round of applause to Thomas for his presentation.
Thank you so much.